I will also try very briefly to share my screen in full screen mode, to check whether everything works, okay?
Yes, yes, please.
Okay, good.
So now you should see the PDF, but not in full screen.
Exactly.
Yes.
And now it's in full screen?
Yes.
Yes.
Yeah,
Okay.
good now, yeah.
Perfect. Then that's it.
So what have you decided? So what have you decided regarding the files that you want to share with the participants? This is happening anyway in the afternoon, right?
Yes, and I think we agreed that Zachary is sharing a link, and I will send him the files.
Yes.
Good morning, Yasmin.
Hi.
Content. Perfect. Okay, so let me try to share my screen. Now you should see the PDF, and now hopefully you should see it in full screen mode. Okay. And do you also see my mouse, which I will use from time to time just as a laser pointer to
Yes.
make you aware of
Yes.
where I'm pointing at? Okay, perfect. So yeah, the day today will be about mixed integer nonlinear optimization, and the day tomorrow will be about bilevel optimization. So let's start with Mi Nlp today. So this is my plan for what you should know at the end of today, after the lectures and after the exercise class. So of course you should know what an Mi Nlp is. What I find especially important is that you learn to distinguish between convex and non-convex Mi Nlp, and we will also see during the more algorithmic part of these talks why this is a very important difference in these two problem classes. That you know something about the standard Mi Nlp modeling technique. So at least in the beginning, I will also show you some examples. And while we discuss these examples, we will see some standard modeling tools as well. And then most of the time, I will focus on the classic algorithms in the field. Okay, I will start first with convex Mi Nlp algorithms, and then we will head over to non-convex algorithms, or better say algorithms for non-convex Mi Nlps. And depending on the time that I have or not have, I will also talk a bit about the standard software tools for modeling Mi Nlps, and will also briefly talk about the classic solvers that are out there and that you can use to solve these problems. Since this is maybe more a program for a week than for a day, I'm not going into the details all the time. So we will discuss some proofs for the convergence and correctness of algorithms, but I'm not able to do this the entire time. So what I wrote here on the slide, at least when it comes to me, I almost never remember the last epsilon, especially when I'm listening to lectures the entire day. But I hope very much that you will, at the end of the day, remember the core ideas. And then I guess the details can be read again and again afterward if you really dive into the specific subfields of what I'm going to discuss. Okay, so that should also mean that, as it's written here, there should be no crying in this compact course. So I tried to have it in a rather soft format. So I do not know what you all have as a background in these fields. So I try to start very basic so that I do not lose anybody too early here, and that there is really no crying here in these 2 days for you. Okay, that's the overview of what I'm going to talk about, but this is already what I already sketched a bit. So I think we can just dive into the first chapter, which is just the introduction to this field. And let's maybe start really with some problem classes and what optimization, or Mi Nlp in specific, is about. By the way, this is, maybe I forgot to tell you, whenever there is any question, just interrupt me. Yeah, when it comes to me, you can just open the mic and ask a question, or if you feel more comfortable with it, you can just pose a question in the chat. I will see this hopefully, and then we'll open the chat and read the question out though, so that we can discuss it. Okay, so for me, it's more important that you really take away the core ideas compared to that I really am done with my 400 clicks of pages that I prepared. Okay, good. So what is optimization anyway? So this is the very general format that I'm going to talk about. I assume that you all have seen something like that. So usually I'm talking about minimization problems. You all know that this is no difference when it comes to maximization. We have an objective function, f. We have the variables that we optimize over, that we try to set so that we minimize this function. And while minimizing this function f here, we of course have to satisfy the constraints. And in the very general format, these constraints can be equality and inequality constraints. Although there is no, I mean, we do not lose any generality if we only consider inequality constraints. So this is what I'm going to do almost all the time today, and also tomorrow, that I'm only writing down these problems with inequality constraints. Okay, but we can have equality constraints anyway. And the feasible set of such an optimization problem, I will denote it with omega here. This is just, as I think you all know, the set of all the points that satisfy all these constraints. Okay, good. So one of the most important questions that you have to answer at the very beginning, if you start with a project and if you model your optimization problem and if you have written it down, is to answer whether this is hard. And the answer is it depends, and it depends on very many things. For instance, if it's a linear optimization problem, so that means that all functions are linear, or are some of them non-linear. What about convexity? We will discuss very much the difference between convexity and non-convexity. Do we only have variables that are continuous, or do we also have integrality conditions on these variables? And this is not something that I will not discuss in detail, if all the functions are differentiable, for instance, but we will see the assumptions that we have to make throughout the talk. And yes, I mean, the first two bullet points here are about linear versus non-linear problems. But you will see during today and also during tomorrow that this is not the crucial distinguishment between the problems that we can study. And there is this famous quote by Rockefeller, who said that the great watershed in optimization today isn't between linearity and non-linearity, but convexity and non-convexity. So it will be crucial for both days, both in MI NLP and in bilevel optimization, to have the right convexity assumptions at the right places of your model so that you can set up rather efficient algorithms. Okay, so this is the problem class that we will focus on today. So this is just a specific instantiation of what I showed you before. So this is an MI Nlp, so a mixed integer nonlinear optimization problem. We still have these n variables. We still have the objective function. And as I said to you before, we are now only considering inequality constraints, but this is without any loss of generality. And we will split the nonlinear constraints from the linear ones. So in what follows, I will mainly assume that all the nonlinearities in the constraints is moved to this constraint vector C, while all the linear equality and inequality constraints are modeled in this bounded and polyhedral set capital X here. Okay, so we assume for the nonlinear stuff, usually that we are at least twice continuously differentiable. And I will try to highlight when I come to the details why we need that. And that this capital X here, that this set is a bounded polyhedral set. So you have some vectors L and U, so that you have these inequalities, these linear inequalities satisfied. Of course, again, you can have equality constraints to define this polyhedral set as well. This makes no difference. Okay, and then, and this is what what makes the problem kind of special, is that out of this n variables that are stated here, we have cardinality of capital I many variables that are restricted to be integral. So this capital I here is just a subset of the indices of the variables, and these are exactly the indices of those variables that are restricted to be integer valued. Okay, Good. So as I already said, this includes maximization, equality constraints, etc. Okay, so this is a very general problem formulation that we can work with. Good. Then, of course, is it important? And my clear answer to this is yes. And the reason is that MI NLPs are almost everywhere. Yeah. So the main reason for this is that today, if we want to model systems that stem hopefully from reality, that you usually have to incorporate two aspects. First of all, you have to incorporate decision making in your model. At least this is the case for maybe most of the models. And for this decision making, you usually use the integer part of your model. You invest or not, you sell a car or not, you build a new gas pipeline or not. These are all decisions that you usually model using integer variables. And you often have physics or economies of scale or whatever effect that leads to some kind of non-linearity in your model. And now I see a question already in the chat. Is our feasible space discrete? Well, yes and no. There will be some pictures and examples for it. I think I postponed this to in a few minutes, because then we will see this at specific examples. If I miss that point in a few minutes, please let me know again. Okay. Good. So what I told you are two reasons for the importance of MI NLP. The other importance stems from a more mathematical reasoning, namely that MI NLP includes very many very important problem classes itself. I mean, an NLP, a QP, an LP, a mixed integer linear optimization problem, they are all special cases of MI NLP. So it's already worth from a higher mathematical standpoint to discuss and study these problems, because you learn about other problem classes right away when you do so. So here's kind of, I called it the MI NLP tree, the classes that are included. This is not comprehensive for sure, but maybe these are some of the most important ones. So on the one hand side here, on the left-hand side, you see the convex part of the MI NLP world. So you have convex NLPs and convex MI NLPs, okay? In this column here, you have all these models where you have mixed integer aspects, okay? In these settings, your feasible set is discrete in some sense, at least for those variables that are restricted to be integer valued. And you have, of course, all the continuous counterparts. So you have the convex NLP as the continuous counterpart for convex MI NLP. And these counterparts will be of particular importance when we discuss the algorithms, because these versions of the integer valued variants of the problem lead to the relaxations that we use all the time when we set up and design algorithms. Okay. And on the right hand side, you see the much harder world of mixed integer nonlinear optimization, which is this world that is non-convex. Okay. And I would define in a minute what non-convex or convex MI NLP means, because the definition is not mathematically very sound, but we will discuss this, okay? So you have the very general problem classes here. Then, for instance, you have the polynomial optimization problems, your mixed integer polynomial programming, where you allow the functions to be polynomials. And then you have, for instance, the quadratic programs, both in the mixed integer and in the continuous setting, where you also have kind of polynomials, but with very restricted degree, of course. Okay. So as I now told you, I guess, for 10 times, that it's very important to distinguish between convexity and non-convexity, let us discuss what this means. So in general, we define an optimization problem to be convex if both the feasible set is convex and if the objective function is convex on this feasible set. And that's mainly the problem that we have with this definition in mixed integer programming, because if you have some variables that are restricted to be integer valued, of course, the feasible set is not even connected anymore, because we are talking about discrete sets in a convex set, or discrete points in a convex set. So the feasible set cannot be convex in the sense of the definition of convexity of sets, of course. So this is like, if you use this very original formulation or definition, then there are no convex Mi Nlps. So in Mi Nlp, we use a slightly modified definition. We say that such an Mi Nlp, this is exactly the same problem formulation that we used before, that we call this a convex program if both the objective function is convex and if these constraint functions C are convex functions. Okay, this is why I changed, I don't know whether you saw this, to less than or equal constraints. I had larger than or equal constraints at the very beginning. If you have larger than or equal constraints here, you need to impose the assumption that the constraint function C is concave, of course, but then I can always talk now with this less than or equal about convex functions all the time. And this then corresponds to feasible sets that are constrained, okay, if you ignore the integrality condition, okay? So if the function f and if this constraint function vector C is convex, I mean, this is a polyhedral set. This is convex anyway. So the intersection then of these two sets will be convex. And then we have an objective function f that is convex on this set. And then we call such an optimization problem a convex Mi Nlp. Okay. So in this definition, we simply ignore the integrality conditions because otherwise there would be no convex object in this class of optimization problems. Okay, this is what I showed you before, and an alternative but equivalent formulation, and this is where we see a relaxation now formally for the first time, is that we call such an Mi Nlp a convex one if the so-called NLP relaxation, which is written here, is a convex program. And how do we get this NLP relaxation? Yeah, you simply forget about all the integrality conditions, okay? And if you then have a program that optimizes a convex function over a convex feasible set, and this is exactly what turns out to be true under the assumptions that we had before, then we call it a convex Mi Nlp. Good. So some words about the hardness of Mi Nlp. So the hardness, informally speaking, of course, stems from the fact that we both handle nonlinearities and combinatorial aspects, discrete aspects, by using the integer variables. And this, of course, kind of leads to the fact that this is an NP-hard optimization problem, okay? The easiest proof maybe is just that you reduce MILP, which is, of course, a special case. And as far as I know, this appeared in Cannon and Monmar in the late 70s for the first time. But I mean, from the point of view of today, this is trivial. Yeah. Even worse, and this is a result by Yaroslav, in the early 70s, if you have a non-convex integer optimization problem, then if you do not impose additional assumptions, this is not even decidable in the sense of theoretical computer science. Okay, so like it's written here, there is no computing device that can compute the optimum for all problems in this class. Okay, the example that was used in this paper was an unbounded quadratically constrained integer program, and this is the same undecidability that you also have, for instance, in mixed integer linear programming. If you do not assume that the set in which your integer values lie, if this is unbounded, then you're directly undecidable. Okay, and that's the same, more or less, or the same reasoning for the nonlinear part of the story as well. So what we do is we kind of try to mimic the classic theorem of Weierstrass. You see him here on the right. That is, we do not only assume that this is a polyhedral set, but that this capital X is compact in what follows in this talk. So we have a polytope, and we know that, of course, all integer feasible points then have to lie in this polytope, so in the sense of a bounded polyhedron. And then, of course, we know we are only talking about a finite number of integer points. And then just by enumeration, you can try to solve these problems. Okay, so this is kind of the setting of Weierstrass. If you go to compact sets, it's not that worse anymore. Okay, and you can do something. Then, of course, regarding hardness, you can also try to ask or maybe naturally ask the question. I mean, it is NP hard since it includes mixed integer linear programming. This is what I told you before. And the natural question is it really harder? And I'm not going into the complexity theoretic discussions here, but I want to give you the intuition why it is somehow yes here, the answer. And to give you an intuition, we briefly have to define, most likely all of you know what this is, what the convex hull of a set is. Okay, so here the convex hull of any set S in Rn is just the points Z that you can write down as a convex combination of all the other pairs of points in the set. Okay, so this is all the points Z that you get as lambda x plus 1 minus lambda y. And then lambda is between 0 and 1, as you all know, and x and y are in S. Okay, this is the convex hull. So, and in MILP, so in the linear world, this convex hull is very important because if we can separate this convex hull of all the integer feasible points, this means that we can solve the optimization problem. This is this famous optimization as separation. Okay, and the main insight is that, of course, if you solve a linear optimization problem, this is what you know from the standard linear optimization theory, is that a solution is always attained at the vertex of the feasible set. So if we take the convex hull of all the MILP integer feasible points, okay, if we know this object, we can optimize over it. This is then just linear optimization. Of course, this directly implies that getting this convex hull is as hard as solving the optimization problem if it is mixed integer. So what we do there is, and maybe this is now the picture that kind of shows what I did not answer before. I mean, think about the linear setting. That is, we do not have these nonlinear constraint functions C here, but we only have this compact polytope, which is this red object here. And then if all the variables here in R2 have to be integer valued, the feasible set is discrete, to answer the question now very precisely, because the feasible set is just the set of integer points in this red polytope. And of course, if you know this blue object that I depicted here on the right, which is the convex hull of all the integer feasible points, then you can solve the LP, the linear optimization problem, over this blue object, and then you solve the MILP. Okay, this is this separation is optimization argument in a nutshell, that you say, well, what can we do with this theoretical insight that we now get? Well, we can try to consider first this original red polytope that we started with. We can solve the integer, the linear relaxation that we get when we just ignore all the integrality conditions. Assume that we then get this vertex here of the red polytope. And then separation means that you try to find, or that you find, a hyperplane, which is the blue one here, so that this point is separated from the convex hull of all the integer feasible points. And if you can do this with every point, then you can iterate this, and then you get a cutting plane algorithm to solve the MILP. Okay, so next we maybe get this point. I mean, if we do not change the objective function, it's not that likely that we really get this point, but just assume that we then get this vertex, and then we cut this off, then we get this, and we cut this off, and then we get this, and so on and so forth. And if you can iterate this with every orange point here, you can show that by this you can solve the optimization problem. This is not the case for nonlinear optimization problems. And this now is the reason for this somehow, yes, it is harder, which is of course not a complexity theoretical statement in a formal sense. So the I think it's an example by Bilevel in one of his papers. You have this objective function here. This is the nonlinear objective function. If you forget about the integrality constraint that you have here, it's a binary constraint indeed, for all n variables xi, then you just minimize the distance to the point 1/2, 1/2, 1/2, 1/2. Okay, it's just like a least squares objective function. So what you have here in R2, this point x is 1/2, 1/2. This is the optimal solution of the continuous relaxation. So of the relaxation that you get, if you do not impose these integrality conditions, which would give you these discrete set of 4 green points, but that you take this cube here, the unit cube in R2. Okay, and if you optimize over this relaxation, then you get this point. And of course, what you then see is that this is not an extreme point anymore of the feasible set of the continuous relaxation. And even worse, it's in the strict interior, which means that you cannot separate it. Okay, and also from an algorithmic point of view, this is one of the main differences, okay, because you do not have these very plain separation ideas. We will have them, but we have to have them on a different problem, and I will introduce this directly on the next slide. And this is the so-called epigraph formulation. So what we can do is we can just move this objective function down to the constraints here, have a smaller than or equal eta here, and then minimize eta. So this is the so-called epigraph reformulation of the optimization problem. And here you know that the optimal solutions always lie on the boundary of the convex set. So you can do something with cutting plane techniques. And we will use this later on as well. Okay, so this will be one of the very central reformulations of the problem so that we can do classic cutting plane methods as well, also from nonlinear programs. Okay, maybe let's discuss some examples so that you can see, okay, what can we do with this problem class? Okay, the first one is what's called best subset selection in linear regression. Okay, so what you have in linear regression is that you have these data points xi in Rd, and you have yi in R. So think about this as something that turns an input into an output yi. If you just think about an input-output system. And what you want to do is you want to parameterize your model of this input-output system by tuning this parameter beta in Rd so that your input fits best possible the output. And that is the classic least squares optimization problem posed first by Gauss. Okay. But what you often do in practice is you don't want to solve this objective function. I mean, you minimize it then, of course, but you want to only use a certain number of these so-called predictors beta here. You don't want to use the entire Rd, but you want to say, I only want to use k of them. And k maybe is, if d is 10,000 before 10, you only want to use a very specific subset of your predictors that are available for your modeling. So you limit the cardinality of your optimization vector beta. And this almost looks like an optimization version of it. So the objective function here is exactly the same. I just wrote out this scalar product here with another sum. And what we then impose is that the support of this vector should be not larger than k. And the support is the indices of this vector for which the respective components are allowed to be non-zero. And of course, this is not really an MI NLP in the definition that I showed you before, because this constraint does not fit the format that we had before. So what we usually do with these things, and this is then already one of the, classic modeling techniques that you use, you introduce a binary variable here for every component of this beta. And the semantic of this variable is that you think about it as that if Zj is 1, it means that the beta j can be used and it needs to be 0 otherwise. And then we have something that we can easily count. To just count the support is not directly possible in an optimization problem, but you can count binary variables, of course. And this is what we then do. We now just count these binary variables and say, well, only k of them are allowed to be non-zero. The objective function, by the way, is exactly the same. And then we, of course, have to model that this semantics here is kind of modeled. And for this, we here use a classic big M constraint, which is another very classic modeling tool in mixed integer optimization. So we have this beta variable here, and whenever, let's take a look only on the left, this is right, on the right-hand side of this inequality constraint. If this z is 0, then beta needs to be smaller than 0. And if the same happens on the left-hand side, you have beta fixed to 0. And otherwise, it's only bounded by these big M values. And the question then always is, how do you choose them so that you really have an equivalent reformulation? But I'm not going to discuss this too much today, because choosing proper big M values will be a big topic of tomorrow anyway. And the questions are kind of the same. Okay, but now just assume that these constants capital M here are large enough. Then you have an equivalent reformulation. And this is now an MI NLP in the problem statement, in the abstract problem statement that I had before on the slides. So, and then, as I said, the first thing that you should ask yourself is this convex or not? Okay, let's discuss this maybe here at this example. I mean, let's first discuss the feasible set, but it's rather easy to see that all these inequality constraints are linear. The variables, by the way, here, it's not really a mistake, but it's also not complete. Z, of course, is now also a variable of this optimization problem if I have this mixed integer reformulation. So beta and Z are my variables, but they only appear linearly in the entire constraint set. So this is a mixed integer linear feasible set. So exactly of the type that I showed you before in this separation example. And this one here is, of course, convex in beta. I mean, you can think about this as the 2 norm squared, and then you know that this is convex. Okay? So this is a convex optimization problem. Maybe one other very classic example is an extended one based on the very classic portfolio optimization problem, which was posed in 1952 by Markowitz. So the setting that we consider is we have n possibly risky assets. For all these assets, we have a mean return vector. Usually that's based on historical data. And you have a covariance matrix. Then, of course, that's a matrix in n times n here. And you have the constraint that you want to have a minimum portfolio return, which is capital R here. And then the classic Markowitz portfolio optimization problem is that you invest all your budget. So all your x variables should add up to 1. E is the vector of all ones, which means that xi is the fraction of your budget that you invest in asset I. Okay. Of course, your investments are non-negative. And the mean return, remember me here was the mean return vector, should be no less than your minimum portfolio return capital R. And you want to achieve this goal while minimizing your risk, and risk is just modeled here as the variance, which is this quadratic optimization objective function here given via the covariance matrix, capital sigma. Okay, so this is the very classical setting. And what you, for instance, today very often consider is what's called cardinality constraint portfolio optimization. It's kind of the same idea as we had before. So we just restrict now the number of assets that we can really use. In the setting before, I could use all n assets. And now I have that I again have a maximum number of assets that can be included in the portfolio. And then you sum up again some binary variable here. And this binary variable here on the right-hand side of these inequality constraints model whether you invest in the ith asset, which means that the investment variable xi is larger than 0. Okay, and the same constraints as before appear here. And again, you can discuss the convexity properties of this optimization problem. And I mean, if this covariance matrix is positive semi-definite, you know from standard theory that this quadratic form, of course, is a convex function. And then this is again a convex Mi Nlp. Okay, good. As I just told you before, we used twice this very standard modeling trick using big M constraints, right? And I didn't tell you in the best subset selection problem whether it is possible to find reasonable big M values. This now here in the cardinality constraint portfolio optimization example is a very easy one when it comes to determining a correct big M. Because I mean, if you know that all your investments are non-negative, and if they should sum up to 1, you know that 1 is, of course, a correct upper bound of all your investment variables. So you can simply put 1 here for this big M, which is not so big then anymore, and yet have a proper reformulation of your problem. So you see, sometimes it might be hard to develop these values specifically for the big M's, and sometimes, as you see it here, it's very easy. Okay, the third one is, but I will leave this for the exercise class in the evening, the so-called k-means clustering problem. Okay, I have these things here on my slide. I will just briefly go over them. And this is the final Mi Nlp modeling that I present to you here in the lecture class. And it will be one of the exercises later on for you to really model these k-means clustering Mi Nlps and solve them, or at least try to solve them for given data that we will provide to you in the exercise class. But I'm going to discuss a bit again the convexity properties here. So as you see, your mu and b here are variables of your optimization problem. So the mu appears quadratically here in this 2 norm squared term, and you multiply this with such a beta variable, which is a binary variable. So you have what's called a bilinearity if you have these multiplication of variables. And this directly leads, at least if you do not rewrite it, to a non-convex Mi Nlp. And we will discuss these bilinearities later on in a bit more detail because they are very important for non-convex mixed integer nonlinear optimization. So, but just to convince you that these general bilinearities really are non-convex functions, so that this really was a non-convex Mi Nlp. So here's the very standard bilinear function f, which is just the product of the 2 variables, x and y. And if you then take the gradient, you get y and x. And if you then take the Hessian, then you get this 0, 1, 1, 0 matrix here. And of course, this is an indefinite matrix. And then we know that this function is not convex. Okay, so you can easily see that this always leads directly to non-convexity. So always be careful when you use bilinearities, although they do not look that ugly at a first glance. Okay. So it's non-convex. So this was the introductory part. So I hope that you have an idea about what is a mixed integer nonlinear optimization problem, what is the way on how we can write it down, and how do they look like for some practically relevant examples. Okay. So what we will now do is we will go over to algorithms for convex Mi Nlp. So I will now discuss 4 algorithms with you. First, the nonlinear branch and bound, then 2 cutting plane methods, and then this NLP based branch and bound, which you can see, I will explain that later in detail, as a combination of the two rationals that we will follow before when designing the other algorithms. Okay, but from now on, we are only considering convex Mi Nlps in this chapter. Okay, good. So let's start with nonlinear branch and bound. Okay. In fact, this is the paper by Land and Doig in Econometrica in 1960, which invented the branch and bound method, at least as far as I know. Okay, and these two women, they didn't consider convex Mi Nlps, but mixed integer or integer linear programs. And in fact, I will describe the nonlinear branch and bound method to you, which can be used to solve convex Mi Nlps by, in 99% of the time, explaining you the MILP branch and bound. And then I only have one slide in which I explain to you what changes if you go to convex Mi Nlp instead of MILP instead. Okay, so these are the two ladies who invented this method. And as I just said, since this very original idea of Land and Doig is more or less completely the same for the convex Mi Nlp problems, we will first discuss the linear part to simplify the notation, etc. And only will discuss what we have to change afterward to go over to the case of convex Mi Nlps. Okay. Oops. So one other simplification, we for the moment assume that all the integer restrictions are binary restrictions. Okay. Later on, again, I will also show you what will change, but this is now the binary case. So the binary linear program is what is program number 1 here on the left-hand side. You have a linear objective function, you have a polyhedral feasible set in which you consider the 0, 1 points as the feasible points of your optimization problem. So again, you have a discrete feasible set. And what we need in branch and bound is more or less, to explain the method, is more or less the same problem. So problem 2 here and its first 3 lines is exactly the same, but we need some more fixations. So we introduce here 2 index sets, capital Z for 0 and capital O for 1, so that for all the indices I in the set Z, we fix the binary variable to 0, and in the set O, we fix it to 1. And of course, we assume that these sets are a subset of all the variables and that they are disjoint, because otherwise you directly get an infeasible point. Okay, so this is the original MILP after some variable fixations. And now I used this phrase already a lot. Here is the formal definition, because we want to kind of prove some things, or at least state some formal statements about branch and bound methods. We need now a formal definition of a relaxation. So if you consider an optimization problem here in a very formally short form, so you just have a convex, no, it's not necessarily convex, it's just a feasible set, omega, and you have an objective function. And if you then have another optimization problem that has a feasible set omega dash here, so that omega is contained in this omega dash. And if the objective function of the other problem is always an underestimator of your original objective function on the original feasible set, then this is called a relaxation. Okay, so you enlarge possibly the feasible set and you underestimate your objective function. And if you do one of these things, you can also do both, then you get a relaxation. And the most famous relaxations in integer optimization are the so-called continuous relaxations. And those you get by just ignoring the integrality conditions that you have inside of your problem. So if we start with a convex Mi Nlp, just forget about the constraints that stand here for the I, then you get a convex NLP, and this is then the convex NLP relaxation. Same for the LP relaxation in integer linear program. Okay. And then for designing good relaxations, we usually have at least two goals. The first one is for designing algorithms that the relaxations should give us a lower bound. This immediately follows from the definition of a relaxation. I mean, if we underestimate the objective function, and if the feasible set can only increase, then we cannot get worse objective function values for the relaxation compared to the objective function values of the original optimization problem. So you always get a lower bound if you solve the relaxation. And you want that this, and this is then what I call a good relaxation, that the bound that you get is as tight as possible. So you want a lower bound that is as close to the original objective function value as possible. And we will later see in the methods why this is a reasonable thing to have in a definition in quotation marks here of a good relaxation. And the other very important thing is that we want to have relaxations that we can easily solve, or at least much easier than the original optimization problem. And this is what I mean here with tractability. Okay, so it should be easier to solve than the optimization problem, which is the original one, and the lower bound that we get should be tight. Okay, so what is the LP relaxation of this problem that we just discussed, in which we already have some variable fixations? So you have exactly the same program here. You just relax the integrality conditions. So X now is in this hypercube and not in the corner, not in the extreme points of this hypercube. Okay, you simply relax the binary conditions. Okay, so, and with this we can state two lemmas, which are the main ingredients on how to prove the correctness of a branch and bound method, which is really not hard to do. So if you have these index sets Z and O as introduced before, and if ZLP is the objective value of the solution of the LP relaxation with those fixations corresponding to these index sets, this was the problem 3. And if you have the integer program formulation and the optimal objective function value, where you did not relax the integrality conditions, this was then problem 2, then you get that you always get a lower bound. Okay, this is what I explained you already before, or kind of proved you before with very easy arguments, that the relaxation always gives you a lower bound on the optimal objective function value of the original program. Moreover, if you have a relaxation that is infeasible, since you only are allowed to increase the feasible set when you go over to a relaxation, the infeasibility of a relaxation directly implies, of course, the infeasibility of the original problem. Okay? So this is what we call the bounding lemma. And this will be one of the 2 ingredients of the branch and bound method. Okay, so bounding we have. If we solve properly chosen relaxations, we can bound the objective function values of our optimization problem that we want to solve. By the way, there is this technical assumption, or not assumption, but second case, that nobody, of course, ensures that these optimal objective function values exist, because nobody ensures that these programs are solvable. If not, since they are minimization problems, in the other case, we set them, these optimal objective function values, to infinity, and then the theorem still holds true. Okay, so this is just for the extreme case that we do not have solutions. Okay, and then we have also that, what I told you before, out of this bounding lemma, we get lower bounds and we can prove infeasibility while proving the infeasibility of a relaxation. And then we have the branching lemma. And this is the second ingredient of branch and bound, or the first one, depending on how you count. Again, you have, by the way, I didn't prove this lemma here, but the proof is one line and reads, all of the statements directly follow from the definition of a relaxation, right? Okay, so there's not really something to prove. Same for the branching lemma. What's the statement? What's the claim of the branching lemma? So you have these index sets corresponding to the variable fixations to 0 and 1. And you assume to be given a feasible, an integer, or here binary feasible point for your still binary constraint problem 2. Then you of course know that this vector x is either feasible for this problem 2 if you put an arbitrary index I either in the one set where you fix everything to 0, or in the other set where you fix everything to 1. And again, we don't have to prove this. This is trivial. Why? I mean, if this variable xi is a binary variable and feasible for the binary constraint program, it's either 0 or 1. So it's either feasible for this or for that problem that we get with these extended or partially extended index sets. Okay, so here's the method, and I think it's not a good idea to discuss this like this. Let's discuss it like that first. And then let's first consider what's called a branch and bound tree and what's really happening in these methods. And then we go over to the formal listing and understand much easier what this formal listing is about. Okay, so assume that we have a mixed integer linear optimization problem as it is written here. So we have some variables that are now allowed to be continuous and some are allowed to be only 0 or 1. So the method starts with that we say we have kind of a register for the best integer feasible solution that we found so far. And best, of course, measured in terms of the objective function value. So at the very beginning, we, of course, usually do not know any integer feasible solution. So the best objective function value that we know in terms of minimization here is plus infinity. This is what we call the incumbent value, the best known solution so far. So what we then do is we solve the LP relaxation of this problem. So I now explain to you what is branch and bound. So the LP relaxation is nothing else but replacing this binary restriction to claiming that Z should be in the real interval from 0 to 1 to the K. So this is the LP relaxation. We solve it. This is the node problem, which is corresponding to the so-called root node, because this will be the root node of the branch and bound tree that we will set up now during the course of this algorithm. So, and usually some of these ZIs that should be binary are fractional. So something strictly between 0 and 1. If this is, by the way, not the case, which is if it's happening in the root node, say the lucky shot in the method, then you are done. Yeah, it's easy to see that whenever you solve a relaxation, and if the solution that you get has the property that it's feasible for the original optimization problem, then you found the optimal solution to the original optimization problem. Okay, you get a lower bound, you're feasible, you cannot get better. So, but assume we did not have this lucky shot yet, but we have one variable that is fractional. What you then do is you first use the branching lemma. That is, you know, you can construct two subproblems, one here LP2 and one LP3. LP2 is obtained by putting I, the index I, into the set Z, so that we fix the variable to 0 in this newly created subproblem. And you put I, on the other hand, into the other set, capital O, so that it's fixed to 1 here. Okay? And you know by the branching lemma that in one of these subproblems, you will still have a feasible solution if you have it here. So you do not lose feasibility if you start with feasibility. So then we have two new subproblems that we have to solve. Assume we first solve LP3 and assume now that we have a lucky shot here. So we get an integer feasible point by solving the relaxation in the node 3. Then we get a finite objective function value for an integer feasible point. Assume it's 10, and 10 is smaller than infinity, so we can update our incumbent, which was done here already. And of course, you can now, it's called pruned or fathomed. You can prune or fathom this node. There's nothing left to branch on. Everything is already binary feasible, okay? So we are not going to explore the subtree that is formally rooted here in this third node anymore because we already have the integer feasible solution. By the way, this will be completely different when we discuss bilevel MILPs tomorrow. So it's important that you also understand what we are going to discuss now, because tomorrow the things are much more different. Okay, but we still have this node here. And here we have maybe after a solution another variable zj which is fractional. So we again branch on this variable. We get two new subproblems. And now assume we first again solve this one here and assume we have another fractional variable and we have a relaxation solution with an objective function value of 12. Now the bounding lemma comes into play. How? Well, if we go on with branching in the subtree that is rooted here in the fifth node, we only impose more constraints in our feasible set, which means that the objective function value, of course, cannot get better anymore in this subtree. But since 12 is already worse than our incumbent 10, we now know that we can prune this subnode or the subtree rooted in this node 5 here as well, because we will not be able to find a better solution there compared to the best one that we know so far. Okay. So this one here in 3 was pruning by integer feasibility. Here we pruned by bounding. This is that we do not go on here is the bounding step in branch and bound. But we still have this LP4 here. We solve it. K was fractional. We branch on ZK. We get these two nodes. We solve the right one. We get an integer feasible solution, another lucky shot. Okay. Assume that the solution is 6. So we get a better incumbent here. But we have to go on here. We branch on L. Then we get an infeasible problem here. What does this mean? This is the third ingredient of branch and bound. So we stopped going on here due to integer feasibility. We stopped going on here by bounding. And we can stop, of course, here due to infeasibility, because we know if we would go on in this subtree rooted at node 8, I mean, we just impose more constraints, and more constraints imposed on an empty feasible set will be still an empty feasible set, for sure. And here we have the integer feasible solution, again, say by lucky shot, or because we have branched out all the integer variables. This one has then the objective function value 8, but 8 is worse than 6. So now we explored the entire tree here. And we know that the solution that we found here in node 7 is the optimal solution of our mixed integer linear program. Okay. Good. Let's go one slide back. This is the listing. So what we did now is that we always maintained implicitly in this tree a set of open node problems that we still have to solve. This is in this set Q here. And this set Q is a set of tuples, or a set of pairs of index sets. Okay, every node is explicitly characterized or well defined by these sets Z and O of variable fixations in the branching boundary. So what we do always, we choose one of such problems, we delete it from the set of open subproblems, we take it out of this set Q, because we know we will solve it in the next step. This was problem 3. And then 3 special cases can occur. First, the problem is infeasible. Then we know we can just continue with the next problem here in the while loop. And we do not have to create 2 new subproblems because they will always be infeasible. So otherwise, we assume that we get an optimal solution. If this optimal solution is not better than our incumbent value U, we can use the bounding lemma to correctly say that we will not find better solutions in this subtree. So we do not create 2 new subproblems and just continue here with the while loop. Otherwise, we know if we are integer feasible in addition, better than our incumbent, otherwise we would have been here. So we update our solution estimation, X star, and the incumbent. And since we are integer feasible, there's nothing left to branch in this subtree. So we do not create 2 new subproblems and again go to the next open problem. And if all this does not take place, we know that we have a fractional variable, choose any of them. Now the branching lemma comes into play and we say, well, put the index 1 on the one hand or on the left hand side of this tree to the sets of variables that you fix to 0, and here in the other part of the subtree to 1. So you created 2 new subproblems and then you go to the next subproblem that you choose. And then you iterate as long as there are no more open subproblems left to be solved. Okay, let me first check. Yes, the question in the chat is, could we be unlucky and have the fractional case appear many times? Yes. That's what's in the extreme case left to be discussed in these last lines here. Assume that it's not only appearing many times, but always. This means that we never updated our incumbent here, which again means that if we go out of this while loop, U still is plus infinity. And in this extreme case, to answer the question, this means that there is no integer or binary or whatever feasible solution, and we return that the problem is infeasible. And if it happens at least once that you encountered an integer feasible point, you at least updated once your incumbent, and then you know that in X star, you have the optimal solution and then you return it. Okay, so it can happen, of course, many times. If it appears all the times, then you are infeasible and you kind of solved the problem because you correctly identified this problem to be infeasible. Next question, good question is, what about unbounded solutions? I will answer this in a minute when I show you the correctness theorem about branch and bound. So first, one more comment on what about general MILPs? So if you do not have that the problem needs to be binary for some of the variables, but just integer valued. So for instance, in this picture, this means that you have these, if xi here is one of the variables that is integer valued, the feasible set is the set of these slices here. in the general polytope. And of course, only in the case if this xj variable here on top is on the y-axis is not restricted to be integer. Otherwise, you would have in this diagram discrete points. So, and if we have such a problem, and if we solve the LP relaxation, for instance, assume we get this point here, we again also compute or set up two new subproblems, but just saying, well, in the one subproblem, xi should be not larger than the fractional variable rounded down, and in the other case, rounded up. So it's more or less the same procedure, but that we do not fix to 0 or 1, but that we just have new constraints to split the problem in this branching process into two new subproblems, for which we know that if there was feasibility at the very beginning, we maintain feasibility during the course of our branching process. And of course, think back to the result by Yaroslav from 73. If you have no finite bounds on this xi, this branching process will never stop, of course. So for this method to be a method that terminates after a finite number of branching steps, you need this compactness. So the set is a polytope in which you have your discrete points, the feasible ones. Okay, so just to give you an example, I mean, this was here in this didactic example and a tiny tree. They get huge in practical applications. So here is a branch and bound tree that was created by Bill Cook, I guess, while he was solving a TSP problem via branch and bound. And you see that every green point here is one of these problems that you have to solve. And you see, well, you have to solve a lot of these problems, usually, if you have a hard optimization problem. So maybe again here as a wrap up. So what we now saw is that in branch and bound, every node of this tree represents what's called a sub-MILP. It's an MILP which corresponds to the original one, but with a finite set of variable fixations or branching constraints. So in every node, we solve an LP relaxation of this sub-MILP. And this is the original LP relaxation plus an additional set of variable bounds or fixations, okay? And what we know is that we have three situations in which a node becomes a leaf of the tree, which is the case if we have an integer feasible point. They give us upper bounds. Feasible points always give us upper bounds. If it's the best upper bound, we can update our incumbent. Then we know also infeasible nodes become leaves of this search tree. And by the bounding lemma, we know that nodes with a fractional solution that have an objective function value that are worse than the incumbent's one, then we can bound this and prune the subtree because we cannot find better solutions there. Okay, so what you get is these upper bounds by feasible points. You get these lower bounds by the solutions of the relaxations. Of course, they are only lower bounds in the subtree that we are talking about, okay? The lower bounds are local information, whereas the upper bounds as feasible points are global information. So if you take the best lower bound, which is then L here, then you can also define what's a very important notion in mixed integer optimization, which is the gap. So here it's the absolute gap. Usually you state it in relative terms. And if you have this absolute gap, which is just upper bound minus lower bound, then of course, you know that if you have a gap of 0, this gives you a proof of optimality. And in this case, this branch and bound tree is kind of a certificate for either optimality or for infeasibility of the integer optimization problem. Okay, so here's the correctness theorem. And here's my answer to the question in the chat. What about unbounded solutions? I simply make the assumption that the LP relaxation of my original MILP, so the LP relaxation that I have to solve in the root node, that this one is bounded. By this, it immediately follows that all other problems will be bounded. So we only talk about infeasible problems or problems that are solved to optimality. Because we know that in linear optimization, you only have 3 cases for an optimization problem. Either you are unbounded, or you are infeasible, or you have an optimal solution. Okay, and by excluding here the boundedness, we only talk about feasibility and optimal solutions. And then by all the stuff that we considered so far, and the branching lemma and the bounding lemma, we know that this algorithm that I showed you will terminate after a finite number of visited nodes, either by returning a global optimal solution or with the correct indication of infeasibility. And there is nothing more to prove because we have all the ingredients that tell us all the stuff that we did is correct. And the only thing that would be left to prove, but this is super easy, is that it really terminates after a finite number of nodes. But if we are talking about a bounded set of finitely many integer variables, let's consider the binary case. You know that the largest size of your binary search tree will be such that if you enumerate the entire tree, you will have 2 to the k many leaf nodes. And then you have some from 0 to k2 over the summation, 2 to the summation index many nodes that you have to solve at the maximum. This is a large number, but it's finite, so the theorem is correct. So the correctness mainly follows from boundedness and finiteness of the number of integer variables. So here's the one slide that shows you how to transfer this idea from mixed integer linear optimization to convex Mi Nlp. Just replace LP relaxations with convex NLP relaxations. So in every node now, we have the original root node relaxation, which is the convex NLP relaxation of our original convex Mi Nlp, plus the variable fixations or branching constraints that we constructed due to branching. That's it. There are some technicalities in order to have optimization algorithms that really can solve these convex optimization problems in the nodes. To global optimality, you usually need that all the functions that are part of your optimization problem are continuously differentiable. And you need to have Slater's constraint qualification satisfied. Just take this for granted right now. We will discuss these constraint qualifications later on in much more detail. Okay, and then we can solve all the node NLPs to global optimality because this is, in quotation marks, easy, at least from the point of view of complexity theory, since they are convex with a constraint qualification, so you can solve them to global optimality, for instance, by first order methods. That's it. That's the first MINLP method maybe that you know. And it's not, more or less nothing else than the classic Econometrica 9060 paper by Land and Doig. Okay. Maybe just one teaser regarding non-convex MINLPs. I mean, of course, one natural question that now might show up in your hats is, well, couldn't we just do the same for non-convex optimization problems? And usually this is not doable because in order to get a proper bounding scheme, you have to solve the problems in the node of your optimization problem to global optimality. What happens if this is not the case? So assume, because it's a non-convex problem, you can only solve this node problem to local optimality. And assume you get a local optimal solution with the objective function value of 42. And further assume that your incumbent is 10. So you compare 10 to 42, and in your classic bounding scheme, you would say, well, if I already have here for the relaxation 42, which is already worse than 10, I don't have to explore the subtree rooted in this node because there cannot be a better solution. But there can be a better solution. Nobody tells you that although you have a local optimal solution with the objective function value of 42, that there is not a global optimal solution with maybe the global optimal value of 5, which would be better than 10. So you would have to explore the subtree. And since you cannot usually in practice solve non-convex NLPs to global optimality, this is more or less as hard as the original problem, this idea does not transfer directly to the non-convex case, and we will later on discuss stuff on how to deal with that. Okay, good. Maybe one or two last notes, and then I will stop for this first morning session. I did not discuss very, very many things that are also algorithmic ingredients of these methods. How to choose the next node to be solved. I just said to you, choose any. Of course, correctness is okay if you choose any, but your practical performance heavily relies on the one that you choose next. Same for the branching rules. Okay, what is the fractional variable that you have to branch on next? Usually you don't have a uniquely determined one, but many of them. This is branching rules. Then you have pre-processing, no pre-processing, cutting planes, heuristics, all that stuff here. And I do not have the time to discuss all these ingredients now in this lecture, but it is very important for the practical performance of the method to have a good idea on how to do these things as well. And if you do this properly, you still get a worst case complexity of this method, which is exponential. But in practice, it turns out that it often performs much better. Okay, so I think we will give you also the slides afterward, at least when it comes to me, you can have them. So there are also some slides where I just list some of the maybe most prominent solvers for the problem classes that I discussed. So here you see, for instance, a list of solvers for MILP. So if you are, for instance, in your PhD project later on in a position that you have to solve such a problem, then you can take a look at the slides and at least know where to go to download the software. Okay, I think at that point we can stop here. And this, Ivana, this was the plan, right? That I go to 10:30, and then we have a break.
Exactly.
So I think this is a good point.
Thank you. This was a very good introduction, and also interactive in terms of the questions that you have received from the audience. So thanks, Martin. Thanks to everyone in the audience. We will make a break now, and we will be back in about 30 minutes, right?
Yeah. Okay.
Okay.
Perfect.
So we will stop recording. You can stay online. All the participants can stay online. We will just turn off the cameras and the videos, and we will continue the session at sharp 11 o'clock. In the meantime, if you have additional questions, do not hesitate to post them in the chat, and then Martin can take these questions at the beginning of the second half.